Hello, this is the next video in a playlist titled General Linear Models Design of Experiments. And this is part 10 of a 10-part little mini-series on one-way fixed effects ANOVA. And here we're looking at partitioning the sum of squares treatment. So in parts 7, 8, and 9 we introduced the concept of contrast, and then orthogonal contrast, and then the normality of contrast. And now we're going to use that and partition the sum of squares for treatment effect. So theorem 1, let's assume we have A minus 1 orthogonal contrast with unique least squares estimates C1 through CA minus 1. Then the sum of squares treatment can be partitioned into the sum of these sum of squares for the contrast. And these were introduced in part 8, the definition of these. Also, the contrast for the ith contrast and the jth contrast, they're all independent under normality. So let's prove this. So lambda I must be a part of the row space, so it can be represented like this for some row I. And that means that M row I has a very specific form, and it's rho star I, and we introduced that in parts 7, 8, and 9. Now let capital P be defined as in theorem 4 in part 9, which are these orthogonal vectors normalized, so these create an orthonormal basis for the column space of M minus J. Now, the sum of squares treatment can be written in quadratic form like this. In theorem 4 part 9, we proved that this perpendicular projection matrix is equivalent to this perpendicular projection matrix, where capital P star is defined like this. Well, now we group these and we group these into this, and this is a vector and this is a vector, so it's a vector product. So that we're going to multiply the same components, so we get a squared, and then we're summing. So these become this, right? So it's this squared, that times this squared, and then the length squared. But this right here, the norm squared, is actually just a vector product. And this right here was how we defined the sum of squares associated with contrast I, which is this. And see part 8 for more detail. So this sum becomes this. So the sum of squares for each of these orthogonal contrasts partition the sum of squares for treatment. And to me, that's a little mind-boggling that it does that. And the proof of 2, let's let the contrast, the ith contrast, be represented as this. Now remember, this, when it becomes a CY, that means it's the least squares estimate of that contrast. Otherwise, it's gamma, I. And then that means what we do is we put the least squares estimate in here for beta, and which is this. But since it's a contrast and it's estimable, that lambda has to be part of the row space. Now these x's create the perpendicular projection matrix onto the column space of X, which we called M. And see part 7 for more detail for this if you need it. Then that means that and also the jth contrast, the least squares estimate of the jth contrast, can be represented like this. Now, so we have a matrix times y, and it's a vector times y and a vector times y. Now since these are normally distributed, right, because the y is normally distributed, then the product of these out front, actually you have to transpose the right one. If this is 0, then they're independent. And then so this transposes this, but this is M. But because they're orthogonal contrasts, this is 0. And we prove that in parts 8 and 9. So thus these least squares estimates of our contrasts are independent. Also, see part 8. Also, I have a video called Independence of Quadratic Forms that kind of helps explain some of this if needed. So theorem 2 is that if there is no treatment effect, so all the taus are equal, I mean, if they're different, that means there's a treatment effect. But if they're all the same, then there's no treatment effect. And that is if and only if all the contrasts of this form are 0. Those two are equivalent definitions. And let's prove it. So let's go back, let's go left, which means we're going to assume that all contrasts are 0 and show that there's no treatment effect. So if all contrasts are 0, then all contrasts of the form tau I minus tau j must be 0, right? Because all contrasts are 0. And this is a contrast, right? So it's a 1 and a minus 1, and the rest are 0. So all those coefficients add to 0, so it's a contrast. But if this is 0, that implies that tau I is equal to tau j, and this is for all I and j not equal, which then shows that they have to be equal. So now let's assume that all the taus are equal, meaning there's no treatment effect, and let's call it tau. Let's represent that number, tau. Then any contrast of this form, we have the following. The sum of the CI tau i's, which is a contrast, but since all the taus are equal, there's no index, so we can take it out front. But the coefficients, the c's, must sum to 0 to be a contrast. So that says that all contrasts are 0, and the theorem is proven. Now the one last note, which I just find intriguing, from theorem 4 part 9, the column space of M minus J can be characterized in the following, which is it's represented by this row star vector, which means it's of the form this. The first n components are C1 over n. The next n components are C2 over n, all the way to the last n components, which is CA over n. Now granted, the CI's have to sum to 0, but this is the representation of this column space, which I find quite intriguing. Anyway, well, that's all I have for this little mini series. Hopefully you enjoyed that. Next, I have a 5-part mini series on one-way random effects ANOVA models. That's coming up. And hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.